In this video, we'll be discussing a simple search problem called rotting oranges. Let's get an understanding of the problem first. You are given a grid of some size, inside which you have a bunch of fresh and rotten oranges placed in non-overlapping cells. As you can see here, there can be empty cells in the grid as well. Fresh oranges are represented by 1, rotten oranges by 2, and the empty spaces by 0. In any given interval of time, a rotten orange has the ability to rot fresh oranges placed immediately next to it, vertically or horizontally. Fresh oranges in the diagonally adjacent positions remain unaffected. Let's assume this is the placement of the oranges at the beginning, time equal to 0 seconds. At time equal to 1 seconds, any fresh orange vertically or horizontally adjacent to an existing rotten orange also gets rotten. So these two fresh oranges get rotten here. At time equal to 2 seconds, another 3 oranges get rotten. After this, we still have a few fresh oranges remaining, but they can't be rotten further as none of them have a horizontally or vertically adjacent rotten orange. The problem wants us to return the minimal amount of time in which all the fresh oranges get rotten. If we have a situation where all fresh oranges can't be rotten, we simply need to return -1. Let's first take a look at some simulations to get an idea how this works visually in different scenarios. In the first simulation, our grid is full of fresh oranges except for the top left one. We start the timer and in about 24 seconds, all the fresh oranges are rotten. In the next simulation, all the oranges are fresh except for the middle one. Here, all the oranges get rotten in just 12 seconds. In this case, only the oranges at 4 corners are rotten, and it takes 12 seconds again to rot all of them. Let's also take a look at the case where some of the oranges can't be rotten at all. As you can see here, there are a bunch of empty cells separating some of the fresh oranges. These don't get rotten at all, and we would need to return -1 in this case. Now let's see how we can brute force a solution here. The idea is to repeatedly traverse the grid and see which oranges can be rotten in a given time period. We go to each of the cells and ask the question, can this orange be rotten in this time period? We do this repeatedly until we either don't have any fresh oranges or we have reached a stage where it is not possible to rot any more fresh oranges. Here is another simulation of brute force approach. We define constants representing the oranges and empty spaces. There are a bunch of helper methods. Get grid size returns the number of rows and columns in the grid. The next three helper methods tells if a cell is empty, fresh, or rotten respectively. Is cell valid tells us if the past cell I, j is valid for the given grid. We make sure both I and j falls between 0 and the number of rows or columns respectively. Get fresh orange count gives the count of fresh oranges in the grid. Get valid adjacent cells returns the valid adjacent cells around a cell. Adding any element from directions to the past position gives you the adjacent cells. So adding 0, 1 would give the upper adjacent cell. Adding 0, -1 would give the lower adjacent cell, and so on. To make sure we handle the cells at corners and edges, we check if the resulting position is valid or not. Has rotten neighbor tells us if the past cell has a rotten orange neighbor. All we do here is get valid adjacent cells and check if any of those are rotten. Is cell valid for rot gives us whether or not a given cell can be rotten. A cell can be rotten if it is fresh and has a rotten neighbor. Finally, the brute method is what gets called by the client. We get the count of fresh oranges and store it in fresh count. We initialize time to 0 and start a while loop which runs until the count of fresh oranges is greater than 0. Inside the while loop, we increment time. Next, we traverse through all the cells in the grid. At each cell, we ask the question, is this cell valid for rotting? If it is, we collect it all in an array cells to rot. Then we iterate through the cells to rot array and rot each of the cells by marking the orange at the position as rotten, that is 2, and decrementing the fresh count. If we didn't find a single orange to rot in our full traversal of the grid, it means that there are no further fresh oranges to rot. So we break out of the while loop. Out of the while loop now, if the count of fresh oranges is still greater than 0, it means it is impossible to rot all fresh oranges. So we return -1. Otherwise, we return the time. The time complexity here would be the time it takes to reach a stage where no further fresh oranges can be rotten, multiplied by the number of cells in the grid. Now let's move on to the optimized solution. In the brute force approach, we were going through the grid cells again and again. We want to reduce the repeated traversal through the grid. There's no point in, for example, traversing through these set of elements. None of them are rotten right now and they can't rot by themselves. So what we really want optimally is to look in the vicinity of rotten oranges because that's where the action is happening. The new rotten oranges can only show up in the vicinity of already rotten oranges. So we go ahead and rot all fresh oranges around these two. Once we are done, you would realize that you don't need to care about these anymore as we have exhausted all fresh oranges around them. There is no need to come back at them. The next set of oranges we need to explore are the ones just rotten in the last step. We explore the vicinity of these rotten oranges and rot these set of fresh oranges. So essentially, we need to remember the oranges rotten in last time interval and do our exploration around them. Note how this is similar to the idea of breadth first search, where we visit the nodes at a given depth before moving on to the nodes at next depth. To perform breadth first search, we would need a queue. We call it to visit next. The element at front contains the position that we would be visiting next. We build the initial queue by pushing oranges that are already rotten at time equal to 0 seconds. Next, we visit the cell at the front of the queue, that is 0, 0, and rot all the oranges that can be rotten from there. So these two oranges get rotten here. We also push these into our queue as we would need to explore these rotten oranges later. Now we are done with 0, 0, so we pop that item from the queue. Next item to visit in the queue is 4, 4. We rot two more oranges, push them to the queue and pop 4, 4 as well. Now the cells at the first depth have been explored, so we would increment time here. The time gets incremented when all cells at a depth are explored, so we would need to know when that happens. We could use a delimiter to know where a particular depth got finished, or we could push the newer items into a new queue and then replace to visit next with this queue. We would see this better in code. We would be doing this repeatedly until there are no fresh oranges remaining, or we reach a stage where some fresh oranges just can't be rotten. Let's quickly go through the simulation. This is a long one. As you can see, we just had to traverse the grid once. No repeated traversals required. It might be the case that we don't even have to traverse the whole grid if the placement of oranges allows that. On to the code now. Most of the things are very similar to what we saw in the brute section. We would be reusing a lot of those functions. Get adjacent cells valid for rot gives all the adjacent cells which can be rotten by the provided cell. If the provided cell is not rotten, it can't rot anything else, so we simply return an empty array. Next, we iterate through valid neighbors and collect fresh oranges in adjacent cells valid for rot array. These are all cells that can be rotten by the pass cell. Build initial queue builds the initial queue. It just traverses through the grid and collects rotten orange in an array. Finally, optimal is the method that would be called by the client. Inside it, we initialize fresh count containing the count of fresh oranges in the grid at the beginning. We mark time equal to 0 and build the initial queue. Next, we run a while loop until the count of fresh oranges is greater than 0 and length of queue is also greater than 0. Inside, we increment time and also have a temporary queue. This will allow us to hold the nodes of the next depth level while we explore the nodes at current depth, the items of which are contained in to visit next. Next, we need to explore the cells at current depth, that is the items in to visit next. We keep popping cells from the to visit next queue, and for each cell, we get the adjacent cells that can be rotten. We then rot them. Rotting happens by marking the cell rotten, that is 2, decrementing the fresh count, and appending this newly rotten cell into our temporary queue for future exploration. Again, temporary queue contains set of cells that would be explored in the next depth level. Finally, we assign Q the value of temporary Q as Q is now empty and we are ready to explore nodes at the next depth. We return the time if all oranges get successfully rotten in the end, otherwise we return -1. The time complexity here is just going to be proportional to the number of cells in the grid, that is m into n if we have m rows and n columns. That's it for this video. Thanks for watching.